Today, we are going to talk about the layers of the Earth. Perhaps you've imagined that our planet is just a giant sphere of earth and rock, and that as you dig deeper and deeper into the Earth, you keep finding more rock and more stone until you come out on the other side. Well, if you think that way, sadly, you are mistaken. Inside the Earth, there are really intense things happening. And when I say intense things, I'm talking about magma, temperatures over 6,000 degrees Celsius, radioactivity, and an internal pressure of over 1 million atmospheres. Today, you are going to travel back to the time when Earth was formed, and thus you will understand its layers. So prepare yourself and turn on your neurons, because we are starting an amazing journey to the interior of the Earth. About 4.6 billion years ago, in our region of the Milky Way, a nebula, which is a large cloud of dust and gas floating in space, collapsed upon itself due to its enormous mass. The materials concentrated, and due to the force of gravity, the heaviest one stayed at the center, beginning to create the sun. The great mass of that nascent sun caused a protoplanetary disk, flattened and rotating around the sun. And then the planets began to form. The theory of planetesimals is the model that best explains how this could have happened. The force of gravity caused the dust and gas floating around the sun to begin to clump together. The bigger the groupings became larger and larger the more mass that they had, attracting more dust, more gas, and more rocks, creating a dynamic in which what were initially just many small particles ended up becoming protoplanets and subsequently planets on their own. For hundreds of millions of years, planets like Earth were attracting the enormous amount of meteoroids that still orbited around the sun, and there were so many impacts that turned the planet into a red-hot hell. This is how it is explained that the interior of the Earth is so hot. The interior of the Earth has a lot of molten iron, but also has many radioactive materials. Finally, we have to consider that the Earth was a molten ball in its origins. When the meteorites stopped impacting, the outer layer gradually cooled, which caused the crust to eventually become a solid and cold layer. But as everything cools from outside to inside, there is still a huge residual heat from when the Earth was formed, which, combined with extremely high pressure and radioactivity of the core, causes the temperature at the center of the Earth to exceed 6,000 degrees Celsius. This is how we understand today's Earth, whose interior is studied based on two models that name distinct layers. The static model focuses on studying the chemical composition of each layer, since the minerals present in each layer vary as we go deeper. And the dynamic model focuses on studying the mechanical behavior of those materials, that is, whether they're liquid, viscous, or solid. So let's start with the static model. The outermost layer is the crust, with a thickness ranging from 3 to 70 kilometers of hard and rigid rock. There are two types of crust, oceanic and continental. The oceanic crust, formed by basalt rocks, is denser and heavier than the continental crust. That's why when an oceanic plate collides with a continental plate, it's usually the oceanic plate that subducts back into the mantle. The oceanic crust is also younger than the continental crust. In fact, the oceanic crust is continuously regenerated through the larger rifts that separate the continental plates. The continental crust is lighter and is made up of granitic rocks that may be covered by sedimentary or metamorphic rocks. It is much older than the oceanic crust, but currently, continental crust is not forming anywhere on the planet, so its formation cannot be studied and its origin is not very clear. The next layer down is the mantle, which is molten and has a thickness of about 2,900 kilometers. The upper mantle is characterized by the presence of minerals such as olivine, and the lower mantle is dominated by minerals such as silicates. The deepest layer is the super famous giant like button. Okay, I'm kidding. But Seriously, if you are enjoying this video, please don't forget to click like and subscribe. Something as simple as this is very, very important for the channel, so thank you very much if you do that. Actually, the deepest layer is the core, made up of iron, nickel, and the super heavy radioactive elements. The outer core, due to the pressure and temperature, is very, very liquid, but the inner core, which extends all the way to the center of the Earth, 6,378 kilometers deep, is subjected to so much pressure that the molecules are so tightly packed that they cannot even be in a liquid state, but rather return to a solid state. In the dynamic model, the outermost layer is called the lithosphere, which is characterized by behaving in a fragile manner when subjected to deformation, meaning that it breaks apart. The lithosphere reaches a depth of between 100 and 250 kilometers. The asthenosphere extends down to a depth of 350 kilometers, and due to having a higher percentage of molten rock, it can move independently of the lithosphere. The next layer is the mesosphere, which encompasses the rest of the mantle. And finally, the endosphere corresponds to the core, which is divided into the same layers as in the other model: the outer core, which is liquid, and the inner core, which is solid. But what if I tell you that the deepest hole ever dug by humans is only 12 kilometers deep? How is it possible that we know what is happening at a depth of 6,300 kilometers? Well, my friends, that's where human intelligence and science come in. We don't need to dig to learn all of this because there are indirect ways to deduce what is happening down there. It was in the Soviet Union where the super deep borehole of Kola was drilled, reaching a depth of 12 kilometers. The rock reached temperatures of almost 200 degrees Celsius, causing it to become viscous, saturated with water and hydrogen, and constantly collapsing inside the borehole. After several collapses, it was realized that the rock was so unstable that drilling could not continue, so the project was simply abandoned. However, even though excavating to the center of the Earth is not possible, its composition can be studied through seismic waves, as the wave velocities change depending on the type and state of the rock. The first seismographs, devices used to record earthquakes, were invented in the 19th century, and by the earliest 20th century, they had spread to many countries around the world. Two types of seismic waves have been identified: P waves and S waves. Scientists had theorized that if an earthquake occurred in one place on Earth, the seismic waves should travel in a straight line at the same speed through the crust until they were recorded in other places. This was the theory, but it was not being confirmed. In reality, anomalies like this were occurring. This could only mean that the Earth was not uniform in its interior and must be composed of different layers. In 1909, a Croatian scientist named Andrija Mohorovičić was the first to explain what was happening. He realized that when an earthquake occurred near the surface, there were waves that traveled near the surface and others deeper down. The ones that traveled closer to the surface arrived more quickly at seismographs located closer to the epicenter of the earthquake, but surprisingly, the deeper waves were the first to arrive at the farthest seismograph. This could only be explained if there was a difference between the properties of the upper zone, the crust, which was solid and rigid, and the mantle, which was viscous and more plastic. The waves took longer to penetrate the deeper mantle, but once they succeeded, they could vibrate more quickly, eventually arriving more quickly at the farther points. This was how the crusts, mantle, and boundary between the two layers, the Moho discontinuity, were established. Shortly after, in 1914, it was Benno Gutenberg who discovered that at a depth of 2,900 kilometers, P waves experienced a distortion in their direction, and that S waves simply stopped. They couldn't penetrate the area at all. The study of wave behavior had shown that P waves underwent variations depending on the state of matter, and that S waves couldn't penetrate liquids. In this way, it can be deduced that at that depth, the matter there must be in a liquid state. A new layer had been discovered, the core, which was completely molten. In the boundary between the both layers, the Gutenberg discontinuity. Finally, in 1936, it was Inge Lehmann who discovered a final deviation in the deepest part of the core, indicating that it was in a solid state, although it seemed illogical. At the time, there was not enough technology to accurately analyze waves that reached such depths. Something was needed that could create a very powerful tremor, so that its waves could be studied accurately. And that something was not long in coming. During the 1960s, the US had already filled the planet with seismographs and took advantage of their nuclear tests to lend a hand in science. Now that the exact time and location of the explosions could be known, waves could be studied with millimetric precision, and that's how it was possible to identify that this new layer, which could be named the inner core, began at a depth of 5,120 kilometers. Basically, studying the way the waves move and comparing it with laboratory simulations, where the speed of waves in each mineral is tested, is how it is possible to infer which minerals make up each layer. All of this is done using logic, our best tool. Using the brain to deduce what we can't directly see. If you've made it this far, please click like. You might be interested in watching one of the next videos. If you love geography and history topics, I recommend subscribing to the channel. And share it with anyone you think might be interested. So thank you so much for watching, and we'll see you next time.